Bismillahirrahmanirrahim. Name of our course is Category Theory. In order to get some motivation, let's discuss about sets. And you know about sets from your intermediate. Even before you have studied sets, their functions, complement of a set, intersection of sets. So you know about sets and their intersection. Union of sets, empty set, universal set, complement, and then you must be remembering De Morgan's laws. Set difference, and so on. So you have studied sets in detail in your previous courses. You must be remembering this symbol which stands for belongs to. You have also studied the functions. A function we mostly denote it as a function from set A to set B is an assignment which assigns to each element A of set a unique element which we denote by FA belonging to set B. So this is in fact definition of a function, and we know that the set A is called domain of the function. Is called domain of the function, and the set B is called codomain of the function. We also have image of set A under function f, which we denote by FA, and this is in fact FA such that A belongs to A. Images of all the elements of set A, which is image of A, or we also call it range of f, range of the function f. Thirdly, we know that for any set A, there is a function called identity function which assigns to each element of set A the same element in the set A. So identity functions. Identity function. for any set A, the function for any set A, the function whose domain is A and its codomain is A as well, and we denote this function by capital letter A, and we write A as subscript just to show that this is identity function from set A to set A, and this is defined as is called identity function. And is defined as FA, it is image of element A of set A under this identity function is going to be the element A itself. So this is the identity function. Then we have studied compositions of functions. So let's discuss what compositions are. In fact, we are recalling these concepts. So composition of functions. So let's consider two functions. If f is a function with domain A and codomain B, and g is a function with domain B and codomain C, if these are functions, then composition of these two functions, then their composition, and this is denoted by G circle F, is defined as we are going to compose these two functions, function f with function g, and their composite function will be function from A to C with domain A and codomain C, and this is denoted by G circle F, and is given by effect of G circle F on any element of set A will be given by applying function f on A. We will get an element in the set B, and then we apply function G on FA, GFA. So G circle FA is equal to G of FA. So this is the way we define composition of two functions. So having said that, we come to a very important law, that is associativity of composition of functions. So associativity, if f is a function with domain A and codomain B, and g is a function with domain B and codomain C, and h is a function with domain C and codomain D. if these are functions, then in fact we can compose these two functions with each other, and having composed these functions, this is what we will get: H circle G, which can be composed with F, H circle G circle F. Or what we can do is we can compose G with F, so this is G circle F, and then we can compose it with H, so H circle G circle F. So H circle G circle F is same thing as H composed with G composition F. H circle G circle F is equal to H circle G circle F. Just note the shift of brackets. Here we have brackets around H circle G, and F is outside the bracket. In this case we have brackets around G circle F and H is outside the bracket. And note that order is same: HGF, HGF. So this is associative law of composition of functions, which is associative law of composition of functions. So that is, composition of functions is associative. Composition of functions is associative. And there is another very important property of functions, and that is, if F is a function with domain A and codomain B, is a function, then note that we can compose this function F with this function from B to B, which is in fact identity function of set B, identity B. This is equal to a function with domain A and codomain B, and this will be written as identity function of B composed with function F, and this function is in fact equal to the same function F, which is with domain A and codomain B. So what we are saying is that if we compose identity function with function F, we get the function F. Just note that we are composing identity function on set B with function F, and we get the same function F. And similarly, we have this function from A to B with domain A and codomain B, the function is F. We can compose this function with identity function of set A, identity function of set A, and this will be the composition: domain A and codomain B, and this is F composed with identity function of set A, and this will again be equal to the same function from A to B, the function F. So what we are saying is that if we compose function F with identity function of A, then result will be the same function F. So that is, we have composed function f with identity function of set B, and we have composed function f with identity function of set A, and in both cases we obtain the function f itself. So this is what we are saying, that identity function of B composed with function f is equal to f, and f composed with identity function of set A is again equal to f. So when we compose the function with identity function of set in domain, we get the same function. And similarly, if we compose a function with identity function of the set in codomain, we obtain the same function again. So these are very important properties. Let's revisit these properties again. We just want to emphasize on these concepts because these concepts are very important in order to understand basic concepts of category theory. So we revisit about data. Let us revisit these concepts. Before doing that, let me comment that we use phrases function, map, mapping, homomorphisms. In fact, these phrases have almost same meaning. You remember that when you study group theory, you talk about group homomorphism. When you study ring theory, you talk about ring homomorphism. When you study topology, you talk about continuous functions. So function, map, mapping, homomorphisms, sometimes we simply say morphisms. These are similar concepts, and the phrases differ in reference to the context we are emphasizing on. When we are studying group theory, we talk group homomorphism. When we study vector spaces, we call linear mappings. When we study ring theory, we talk about ring homomorphisms. So what we have to devise is a notation. In fact, let me explain it. Let A and B be two sets. Then, in fact, what we are interested in is we are interested in all those functions which have domain A and codomain B. So in fact, we are interested in set of all the functions with domain A and codomain B. This set may contain only one function, sometimes it may be empty. So this is the set we are interested in. Different books use different terminology in order to represent this particular set. In our course, we will use this notation, home AB. Home, this phrase comes in fact from homomorphism. So home AB means in case of sets, home AB where A and B are sets means set of all the functions from set A to set B, or set of all the functions with domain A and codomain B. So this is our notation for the set of all the functions from set A to set B. So having said that, so first of all, we are interested in collection of all the sets. So collection of all the sets. Secondly, for any sets A and B, for any sets A and B, we have home AB, which is in fact the set of all the functions with domain A and codomain B. Functions from set A to set B. So this is home AB. And thirdly, for any set A, for any set A, there exists a function with the domain A and codomain A as well, and this is the function we have already discussed, identity function. So for any set A, there is always a function with domain A and codomain A. In fact, what we are saying is that home AA in general, this is not empty. There is always one function which is identity function in it, and let's emphasize that this identity function belongs to home AA. Note that if A and B are two different sets, then home AB may be empty, but if you take functions from set A to set A, then this set is never empty because identity function is always there. So having said that, let's come to this concept, composition, for F belonging to home AB. We simply mean that F is a function with domain A and codomain B, and G belonging to home BC. We simply mean that G is a function with domain B and codomain C. There exists a function, we write it as G circle F, and this function belongs to home AC. Composition of these two functions is a function with domain A and codomain C. And next, let's discuss the associativity of composition of functions. So for F belonging to home AB, that is F is a function with domain A and codomain B, and G belonging to home BC and H belonging to home CD. H is a function with domain C and codomain D. We have this particular rule that H composed with G and then this composed with F is equal to G composed with F and then this composed with H. So composition of functions is associative. And finally, if we take a function f belonging to home AB, which means that f is a function with domain A and codomain B, we have identity of B composed with F is equal to F and F composed with identity of A is equal to F. That is, when the function f is composed with identity of set in the domain, result is f, and then the function, when a function is composed with identity function of the set in codomain, then the result is again the same function f. So we have discussed the same concepts which we started with. We only introduced a notation that is home AB, which means that set of all the functions with domain A and codomain B. And using this particular notation, we were able to say things comparatively more easily and in more precise way. So what we have said so far, these are ingredients for the category of sets. So let me comment that. Let's write it as conclusion. The ingredients listed above, or the data listed above, the ingredients listed above define the category of sets. The category of sets. We can recall these ingredients because in fact this particular example is the simplest example for concept of category. So note that first of all we have collection of sets. Secondly, for any two sets we have home AB, the set of all the functions with A as domain and B as codomain. And then for any set A, there is a function called identity function with domain A and codomain A. That is, home AA is never empty. And then if we are given a function with domain A and codomain B and another function with the domain B and codomain C, then we can compose these two functions in order to obtain a function with domain A and codomain C. And then we have noted that if we are given three functions, f with domain A and codomain B, g with domain B and codomain C, and h with domain C and codomain D, then their composition is associative. So a composition of functions, if defined, is associative. And then if we are given a function with domain A and codomain B, and we compose f with identity function of A, we get f. Similarly, if we compose f with identity function of set B, we again get f. So these concepts together define the category of sets. We shall denote this category as, we shall denote this category by we will write capital S, capital E, and capital T. Different books use different notations. Some books use bold letters, but when we are writing with the marker or with the pen, then in fact this is the comparatively better to write all letters in capital in order to see that we are talking about category. So as far as formal definition is concerned, we will give this definition at some later stage. First, let's discuss a bit more about concepts which are very crucial to the definition or formal definition of a category. So we will define category. We will give formal definition of category. Later, and we'll discuss more examples. So we will do it very soon. Before doing that, let's discuss few concepts and see how these concepts look in the category of sets. So now we discuss few important concepts. And see how these concepts look in the category of sets. So first of all, we are going to discuss a very simple concept, and we very well know this concept, and that is concept of onto functions. So before coming to this concept of onto functions and then one-to-one functions, let me comment that in category theory mostly we think in terms of arrows. When we study set theory, we discuss or we prove our theorems by using elements of the sets. But when we study category theory, we try to state our results in terms of arrows and prove our theorems by using arrows. Let me tell you what we mean by arrow. This is arrow. this identity function from set A to A is represented by this particular arrow. This is again arrow. So what we are going to do is we are going to learn thinking in terms of arrows. Thinking in terms of arrows. And we discuss it by using concept of onto functions, concept of one-to-one function, and other concepts as well. So let's first come to onto functions. Onto functions. Let me recall the concept of onto function for you, and you already know what this concept is. I'm simply recalling the concept. So let me recall the definition of function. F from set A to set B. A is domain, B is codomain. So a function f is onto functions are also called surjective functions. We will call it onto mostly surjective. So a function is onto function if for any B belonging to B there exists A belonging to A. In fact, there exists A belonging to A such that fa is equal to B. This means that every element of the codomain is image of some element of domain. So this is the definition of onto function, and we can say it very simply by saying that image of A, fa, we have discussed what fa is. So fa is equal to B. Image of fa is the whole set B. So this is in fact definition or concept of onto function. So let's see a few very simple examples. Let the set A is equal to 1, 2, 3, 4 and set B is equal to, let's say, X, Y and Z. So these are elements of set B. Then the function, let's call this function f from A to B defined as so let's see, this is set A which has elements 1, 2, 3, 4 and this is set B which has elements X, Y and Z. The function f which we are going to define is, this function is going to take 1 to X, 2 to Y, 3 to Z and 4 to Z. This function is onto function, is onto function. And in this case, note that FA is equal to the whole set B. Each element of B is image of some element of A. So FA is equal to B. So this is property of onto functions. Let's take another example, that is counter example in fact. A function which is not onto function. So let's define this function. Let's define another function from the same set A which we have written above to same set B which we have written above, and let's call this function G, and let's define this function as this is set A, this is set B. Elements of set A are 1, 2, 3, 4 and elements of B are x, y and z, and let the function G takes 1 to x and 2 to x as well. Let's this function takes 3 to z and 4 to z as well. So note that this function is not onto because this element y of B is not image of any element of set A. Then G is not onto. This is not onto function, and we note that in this case FA is not equal to B because FA is x and z only, y is missing in FA. So this function G is not onto function. So having said that, let's take few examples about real valued real functions. The function f from set of real numbers to set of real numbers. Domain is set of real numbers, codomain is set of real numbers given by fx is equal to x cube, x raised to power 3, is an onto function. This is an onto function, and the reason is because for any B belonging to R, for any B belonging to R, in this case R means codomain. So for any B belonging to codomain, there exists B raised to power 1 upon 3 which belongs to R. This is domain, such that if we apply this function f on B raised to power 1 upon 3, result is b raised to power 1 upon 3 raised to power 3, because this is the way this function is defined, and this is equal to b. So every element of R taken as codomain is image of some element of R taken as domain. So this particular function is onto function. Let's take a counter example. There are very interesting functions in trigonometry. So let's consider this function, the function sine. We know that domain of sine function is set of real numbers, and codomain is set of real numbers as well. This function is not onto. This function is not onto because we know that range of sine function is equal to this closed interval from -1 to 1, and this closed interval is not equal to R, which is in codomain. So sine function is not onto function. Similarly, cosine function is not onto function. You can think about tangent. In fact, you have to be very careful when you think about tangent, because there are points on real line where tangent is not defined. But anyway, you can find many examples of functions from real analysis which are onto, and there are many examples of functions which are not onto. As you have seen that fx is equal to x cube is an onto function, and the sine function is not an onto function. So note that what we have done so far is we were discussing onto functions with the help of elements. So the approach we have adopted so far is element wise approach. So we have discussed onto functions by using elements of domain and elements of codomain. Now the question is, can we discuss onto functions without mention of elements? So let me ask the question. Can we characterize onto functions without mention of elements of domain or codomain? So this is a question, in fact, and we are going to discuss this question in a bit detail. So our first part of discussion is this particular proposition So the proposition says that if f is an onto function, f is a function from domain A to codomain B. So if f is an onto function, then G circle F, G composed with F, and H composed with F, if these two are equal, then G and G composed with F is equal to H composed with, if G composed with F is equal to H composed with F, then G is equal to H. So this is if a function f is onto, then if G circle F is equal to H circle F, then G is equal to H. Let me simply comment that whenever we talk about composition of two functions, we always keep in mind that this composition is defined. It is very important, because if we are given any two functions, it is not necessary that their composition is defined, because in order to have composition defined, what we should have is that the function f can be composed with function g if codomain of f is domain of g. So this is very important condition. Function f can be composed with function g if codomain of f is equal to domain of g. So whenever we talk about composition of functions, we assume that this particular condition is satisfied, that is, the composition is well defined. So we do not write again and again that composition is well defined. We have in our mind that when we write G circle F, it is defined. Conditions are satisfied. So anyway, if f is a function from A to B, this function is onto, if this function is onto, then composition of this function with G and composition of this function if H with H, if these two compositions are equal, then G is equal to H. It becomes comparatively easier if we draw a diagram, then things look comparatively simpler. First of all, let me write it, where G is function from B to C, and H is again function from B to C. In fact, this is that thing which I was simply emphasizing, that when we write composition of functions, we mean and we assume that that composition is defined, that condition are satisfied. But anyway, we have written these conditions here as well. Let me write in bracket what I was meaning, that such things become helpful. Note that we have a function from A to B. A is domain, B is codomain, and F is the function. F is a function. Then we have two functions with domain B and codomain C. One function is G and the other function is H. Some authors write these functions as parallel functions because they have same domain and same codomain. But anyway, now you can see that we can compose G with F, G circle F, and H with F, H circle F. Mostly in category theory, when we draw this diagram, this particular diagram, this means, let me write it, this particular diagram means, this means that G circle F is equal to H circle F. In fact, in category theory, whenever we draw this particular, we will discuss about these concepts in detail in our coming sessions, but for the time being I do not want to use that terminology which may confuse you. If we draw this diagram and we decide among ourselves that whenever we draw this diagram we will mean that G circle F is equal to H circle F. So this diagram means G circle F is equal to H circle F. Then the result I have written above simply says that if this diagram is there, then G is equal to H. So it is comparatively simple to see it now. If G circle F is equal to H circle F, then G is equal to H. And this is for onto functions. This is what we are going to prove, that if F is an onto function, then G circle F is equal to H circle F will imply that G is equal to H. We will prove that. So let's come to its proof, that if G circle F is equal to H circle F, then G is equal to H. So let's come to proof. So for proof, note that if this function F is an onto function, then so if this function F, we are given that this function F is onto, so we are given that the function F with domain A and codomain B, F is onto. So this is what we have been given. Now suppose that we have to prove that if G circle F is equal to H circle F, then G is equal to H. If this happens, then this happens. So we suppose that this happens. So suppose that G circle F is equal to H circle F. Let's call it 1. Suppose this is the case. We shall prove that G is equal to H. So in order to prove this particular result, let's take an element B which belongs to B. Note that B is domain of G and B is domain of H as well, and we have taken an element of B. We will prove that effect of G and effect of H on B are equal. So then G and H will become equal. So let B belong to B, then now note that B belongs to B, but this function F is onto function, therefore there must exist an element A, small a, in capital A set, so that effect of F on that particular element is equal to B. Then there exists A belonging to A such that FA is equal to B. And reason is very simple, because F is onto. If a function is onto, then every element of codomain will be image of some element in the domain. We have chosen an element B in the codomain, so there must be an element in the domain, so that F image of that element A is equal to this element B. So this is because of F being onto. Then from one, this one, take effect of G circle F and H circle F on this particular A. Then from one, G circle, effect of G circle F on A is equal to effect of H circle F on A. And therefore this means that G of FA is equal to H of FA. This is what composition means in fact. And therefore now note that FA is equal to B. Therefore G of B is equal to H of B. So this means that effect of G and H on B, effects of G and H on B are same, and B was any element of B. So therefore the function G is same as function H, and we have established that. This is what we had to prove. So we have proved that if G circle F is equal to H circle F, then G is equal to H. So sometimes we call it that if a function is onto, then it is cancelable from the right hand side. G circle F is equal to H circle F implies that G is equal to HV. In fact, this is not cancelling, just to give you mental help. Cancelable from the right. Simply we say it mostly. So anyway, we have proved that. Now we can prove converse as well. So we can prove converse as well. We can prove converse as well. And let's see what that converse is going to be. Let's write it as proposition. So we are going to prove that let F be a function with domain A and codomain B. Let this be a function such that G circle F is equal to H circle F implies that G is equal to H. Then F is onto. Note that in our previous proposition we assumed that the function is onto and proved that this condition implies that G is equal to H. Now we are going to assume that this condition implies that G is equal to H, and we will prove that F is onto. So this is converse of our previous proposition. So let's come to proof. So we have to prove that f is on 2. So we have to prove that f is on 2. We will prove it by contradiction. So on contrary, suppose that f is not on 2. On contrary, suppose that f is not on 2. So having suppose that f is not on 2, and we know that if function f is not on 2, then there must be an element in the codomain which is not image of some element in the domain if it is not on 2. So suppose that f is not on 2, then there must exist an element, let's call it b1, in the codomain b, such that b1 does not belong to fa, which means that b1 is not image of some element of a. So b1 does not belong to fa. So now pick an other element of b. In fact, you can pick any element of b. So pick any element, let's call it b2, belonging to b, so that this element b2 must be different from b1, so that b2 is not equal to b1. So take another element b2 from the set b which is different from b1. Now consider following functions. Consider following functions. First of all, the first function we are going to consider is just the simple function identity on b. So consider this function identity of set b, a function whose domain is b, codomain is b, and this takes any element of b to itself, identity function. So this is the one function we have considered. And secondly, we devise a function h, again with domain b and codomain b, by saying that defined as effect of h on any element of set b is equal to same element b itself, provided b is not equal to b1, and the effect of h on b is equal to b2 if b is equal to b1. Let me emphasize it, that is, if we apply h on b1, then the result will be b2. This is what we are saying, in fact. So note that this function h is in fact almost the same identity function ib, because effect of h on b is equal to b, except for b1, effect of h on b1 is equal to b2. effect of h on b is equal to b2 if b is equal to b1. So this function h is almost identity function on b except for one point, and that point is b1 where effect of h is b2. So having said that, it is clear that identity function on b and this function h, they are not exactly the same. They are almost same, but at one point they are different, so we can't call them they are same functions. So they are not same functions. So let's note this particular point. But note that if we compose identity of b with f and we compose h with f, these two results will be same. Now you might be surprised why this is going to happen. In fact, the reason is b1 is not in the image. Remember that our function was f was from a to b, and suppose this is image of the function. b1 is outside this. b1 is outside this image. Therefore, when you take composition, being b1 outside will make these two equal. You can do it by yourself. So these two are equal because b1 is not in the image. So that will not affect their equality. And I have told you that h function is almost same as identity function except at b1, and since b1 is outside the image, therefore these two will be equal. You can draw the diagram and you can see it very easily. So identity function composed with f is same as h composed with h, and therefore now let's come to the hypothesis of our proposition, which says that if compositions are equal, then f is right cancelable, then g is equal to h. Now note that these two are equal, therefore f is right cancelable, so identity of b is equal to h, and therefore identity of b is equal to h, and this is because of hypothesis given in the proposition. Because of hypothesis or condition given in the proposition. In the statement of proposition. Since these two compositions are equal, therefore identity of b is equal to h. So this is because it is given in our statement of the proposition. But this contradicts one. In one, identity on b is not equal to h because they are different on b1. But doing this thing, we see that identity is equal to h. So which is contradiction? Which is contradiction to 1. And therefore our supposition is wrong. We suppose that f is not on 2. So therefore our supposition is wrong. And therefore f is on 2. F is on 2. So this completes the proof. So let's see what we can conclude from this. So our conclusion: a function is combining these two propositions. This is our conclusion. A function f with domain A and codomain B is onto if and only if G circle F is equal to H circle F whenever defined, in fact, implies that G is equal to H. We may say that F is right cancelable. Let me comment it. We may say that F is right cancelable. It's not very careful phrase, but anyway it helps sometimes. F is right cancelable. So let's note that. So in fact we may take G circle F is equal to, we may take G circle H, G circle F is equal to H circle F, implies that G is equal to H as characteristic property, as characteristic property for the function f to be onto. So, and this characteristic property is free of mention of elements of the sets. This property is free of mention of elements of the sets. Let me emphasize that if this property holds, then the function f is onto. If G circle F is equal to H circle F, always implies that